Okay, so we're in section 15.7. And we're talking about triple integration when we have some variable bounds thrown in. So type 1, this is right from your textbook. The picture actually is not terribly helpful, but if you have some surface here, remember that in 3D space, our domain, if it's not a rectangular prism, aka box, then you're going to have some variable bounds. Just like in a double integral, if it was not a domain that was a rectangle, then you had to do the variable bound thing. So in 3D, if it's not a box for your domain, then you have to do variable bounds somewhere. So kind of the most natural thing turns out to be that you're given a surface Z as part of that. That's in terms of X and Y. And so if that's the case, we're, again, just talking about the bounds here, which is a major ordeal in solving these problems, is just the bounds and setting up the limits of integration correctly, or the little numbers and functions. So anyway, what's going to be most natural is if you're given some bounding curve that's Z in terms of X and Y, then you'd want to set up your dz on the inside of your integral. And then it's going to be in 3D space, but it would be a top minus bottom curve. And so that's going to be probably make more sense with an example. So anyway, once you take care of that innermost set of the triple integral, then on the outside, notice that it's a little hard to see, but there's a d there with the double integral. The rest of this is the double integral that we did before. And so here's where we took care of what was going on with respect to z. And so then our domain space that's left for the double integral on the outside is in the xy plane. So that's the part of the picture I want you to kind of notice, is that we got this 3D blob there, and then z can be represented in terms of x and y for the bottom and the top of that thing. And then projecting down onto the xy plane is d. So you set up the rest of that integral on the outside, that outer layer, the double integral, just like you did before. So it's adding another layer. The triple integral is adding like an inner layer of things we have to take care of, but the outer part is the same. So here we have these subtypes, 1 and 2, which again, you're not going to have to memorize any of this or really know. I'm just trying to give you an idea of how these can kind of look. So we could have a scenario where instead of just having numbers for x or y, in other words, our domain is rectangular in the xy plane, maybe we have to do that stuff that we did with the variable bounds with the double integral, just like you've been doing. So that's what subtype 1 and 2 have to do about. And you would just graph that domain in the xy plane like you did, hopefully, on the homework to figure out what's going on there. So we didn't go over the types when I went over double integration, but there were 2 types. And now because we're doing an integral in 3 with a domain that's like in 3 space, then our E, which is kind of the general name now for that 3D space, E. It's called B if it's a box, but it's not always a box, then it's E more generally. We have 3. So we have 3 types going on here. Less natural, the Z, having the top and the bottom surfaces defined by Z is more natural. But the other ways that might be helpful are first integrating with respect to X or Y, and that's where it's easier to characterize X or Y in terms of Z in X or Y. And they'll be oriented in a way, a lot of times you're given the equation. And so what you're looking for usually is whatever function with the bounding domain thing in 3 space is given in terms of X and Y. Like let's say Z equals X squared plus Y squared. That's all set up so Z is a function of X and Y, right? That means you integrate with respect to Z first on the inside. So these problems could get super, super complicated and nightmarish, but they're just doing the triple integral alone is kind of a lot of work. So they're going to be kind of simple. You're going to be able to tell it's not going to get as complicated as it could. So that's why it's kind of good to be, kind of know what to expect with those types, but don't let it be intimidating. All right, let's actually look at a problem, a real one. So we're evaluating the triple integral over e of 2x. E is the region under the plane 2x plus 3y plus z equals 6 that lies in the first octant. So here we're given that plane in the first octant, and what this is the domain here is that solid underneath that plane in the first octant. And so usually the order of integration is in terms of the 2x, how it's easier to integrate that. We're not going to worry about that for now. Really, most of the work with this is figuring out how to set up the limits of integration. So your first thing that you should turn to is, can I integrate with respect to z first? Can I have z be my innermost integral? And if you have a picture, what you're looking for is, can I define a top surface minus a bottom surface and have that characterize the volume? There's not like two planes defining the top, for example. So notice we have that cool rainbow triangle plane that is defining the top, and then what would be the bottom? Z equals what? We did in terms of z. It's the first octant, so that means z equals 0, right? So the bottom is z equals 0, or the xy plane, and so that's pretty much your limits for the integral in terms of z, and that worked just fine. All right, so here the equation was not given in terms of z. Let me scroll up here, but it's easily solved for any of the variables, but z is what's most natural. And so again, this one can be done lots of different ways, it turns out, but it's probably going to be more familiar to do in terms of z if you can. So now we got our bounds for z. 0 on the bottom and 6 minus 2x minus 3y on the top. So you could actually write out that first innermost integral if you wanted to, or just kind of keep building. Now we got to characterize d. Now because we took care of the z stuff, our domain d is in the xy plane. And so that's going to be what shape, again, hint, hint? A triangle. And so just like you would do with the double integral, it's like we're just starting the double integral work now. So these are a lot of work, is to graph that domain. So in your equation, you could set your z equals 0 to figure this out. The intercepts are shown there, so somehow characterize that line. One way is express y in terms of x as negative 2/3 x plus 2. And this is not a rectangular domain. So actually that equation 6 in the red box I got up there, we started on that, but it's one of the more complicated ones, the subtype 1 or 2. So, but it doesn't matter. You don't have to figure that out ahead of time. It's sort of the point I'm trying to make here. It's like, well, okay, what is my innermost integral going to be in terms of? It's going to be in terms of z. That's working. I keep going with it. And now we get to a point where my domain in the xy plane is a triangle. Okay, I know how to do that. I know how to do double integrals, right? So now you just start handling that outer double integral just like you would have on homework. And you're going to have a variable bound because it's not a rectangle. So it turns out it doesn't matter what order in this one again. Do you want to put your variable bounds in terms of x or y? So this is very similar actually to the one we did with the surface area. We usually write our equation for the line y in terms of x, so it's kind of set up for that. And so notice that if you look from the least to the greatest, that our y equals 0 is going to be the bottom line, and then it goes up to the line negative 2/3 x plus 2. So now we're on the easiest layer, which is we're just going to have numbers now in terms of our misfit x that didn't have special attention. And we just look at the extent of x. So it goes from 0 to 3. Those are going to be the numbers that we put in next to the integral having to do with x. So we worked all that out, and that was a lot of work. Now we can finally just write the bounds of the integral. It's a lot of work, isn't it? So it's like that work you did for the on the homework again for the domain D, and now it's like you have that whole Z you got to do too. But we won't give you really hard ones with the Z thing. So now you just evaluate this thing. So we start with the innermost here. Notice again, because of the variable bounds, you cannot have those fun options of doing shortcuts and whatnot. You just got to do it in the order that's indicated. So doing the innermost first, 2x is held constant, and then I have z as my integral with respect to z. And then you're going to plug stuff in for it, just like you would have before. Simplify, and then you muster up enough strength that now you're going to try to work on an integral with respect to y, because that's the next layer out. And so remember that the x's are held constant, so you can go ahead and do that integration with respect to y. Then plug in, and now things are starting to get kind of tedious. So, but you keep going, and now you have lots of simplifying to do. Algebra all day long here until you get to this nice simple answer. And now this integral with respect to x is easy. And so we do that integral, plug in our numeric bounds, do our Calc 1 integral there, and then we're finally done. And we just got little old 9. So we're going to call it a week there, and then we'll save that for some time. I will send an email about